Hello and welcome to this installment of Physics in a Flash. Today's lesson is about average speed number 2. It's actually lesson number 3, and it is about average speed number 2. And it's part of a bigger question of what is average speed? What does average speed mean? There are two formulas for average speed. The one formula can always be used. It is always true. The second cannot, and that is this one. It cannot always be used. In fact, we'll put it right here, right now. It can only be used when the acceleration is constant. Now, when acceleration is constant, it can be any number. 1, 2, 3, -1, -2, -3. It can also be 0. So when we say the acceleration is constant, it can have 0 acceleration, which means the speed stays the same. And the formula can be used then. All right, so where we are here is our basic definitions formulas. We have our average speed formulas. This is number 1, and this is number 2, the subject of today's lesson. So let's first take a look at the anatomy of this formula. What are the quantities? And again, we have three adjectives that we can use to describe every physics quantity. There is initial, there is the average, and there is the instantaneous, which includes final. So in this case here, the average, the symbol we have over the V means the average. This V means the instantaneous, or the final, and this means the initial. Now, what is not necessarily obvious is where this formula comes from. And so let me give you an example like this. At the beginning of the day, a student had 3 bottles of water. And at the end of the day, they had 1 bottle of water. Well, if we took those two numbers, 3 plus 1, and divided it by 2, we would get 4 over 2. What we would have just computed is the average number of water bottles during the day. We took the two things, added them together, divided by 2. That's the average. We might also say that a person, started out at 36 inches tall, and a year later they were 42 inches tall. Well, if we took that 36 plus 42, divided it by 2, that would be 39 inches. And that meaning then is it's the average of the heights. In this case over here, it's the average of the number of water bottles. Over here in this formula, it's the average of the speeds. And this is only meaningful or helpful when the acceleration is constant. That's what it means. It means the average of the speeds. Let's just take a look at the formula from a dimensional analysis perspective. So we have V bar equals v plus v0 over 2. And so we might then have some number, let's say 4 meters per second plus 1 meters per second over 2. This 2 has no units. So then we're left with 5 meters per second over 2, or 2.5 meters per second. Again, the numbers we have in this don't matter. We have some number of meters per second plus some other number of meters per second gives us meters per second. We divide that by 2. We still have a meters per second. So the formula works in terms of its dimensional analysis. Now let us rearrange the equations, because hidden in every equation is our series of permutations of that formula. So we have v bar equals v plus v0 over 2. And let's now solve for this v. So to keep the equality true, whatever I do to one side, if I do it to the other, will keep the equality true. So to simplify this, I want to get rid of this 2. So I will multiply both sides by 2, which gives us 2v bar equals the quantity v plus v0 times 2 over 2. And we're left with 2v bar equals v plus v0. Now, if I'm solving for the instantaneous velocity, I'll do the same thing to both sides, minus v0, and we're left with the instantaneous speed is twice the average speed minus the initial speed. So we now have a second equation, a reworked version of this one above. So we now have v equals 2v bar minus v0. So that's our second equation. And now we'd like an expression for v0, a v0 equals. So let us start with the original equation. V bar equals v plus v0 over 2. And we'll do the same thing to both sides to keep the equality true. And we're left with 2v bar equals v plus v0, exactly what we had in the first case. And now we're looking for v0. So we'll do the same thing to both sides. And we're left with twice the average speed equals, twice the average speed minus the instantaneous speed equals v0. And that gives us our new expression. So we have 3 expressions, and let me just rewrite this one here so we can compare it. And those are our 3 expressions. And as we've seen before, there is no utility in knowing any other version except the first one, because you can solve. But that's how we would do the algebra to come up with those different expressions. Now let us apply this in an example. Let's see, we have our friend Matt, who is in North Salem, and he walks for 10 hours, like so, and he ends up in Newark. Hey, wait a minute, this looks familiar. So we have 10 hours, and he travels 50 miles. So you see I've got my time, I've got my distance, and then from Newark, he has a 2-hour layover, so he waits there 2 hours. And if he's there just waiting, then he has traveled 0 miles. And then after those 2 hours are up, he gets on a plane, flies to LA, a trip of 4 hours. And we are told that the speed is 650 miles per hour. So we have our thread of average speed, we have our thread of distance, and we have our thread of time. Now, what we can see then overall is that this whole affair lasted 10 plus 2 plus 4, or 16 hours. So we have our total over here. We don't know the total distance traveled, and we don't know the average speeds for all of them. So we're missing a value of the average speed here, the average speed here, and we are missing a value of the distance here, all of which we can find rather simply by using our fundamental definition that is always true. The average speed is always the distance, total distance over the total time. So 50 miles over 10 hours is 5 miles per hour. So we have 5 miles per hour. And now we can go to our second case. Here, when we were at Newark, the average speed is total distance over total time. We have a distance of 0 miles, and the time was 2 hours, so the average speed was 0. Well, that should make sense if you're not going anywhere. So 0 miles per hour. And then lastly, we can apply it for the trip to LA, is the total distance divided by the total time. And since we don't know the distance, that's what we're looking for, we will solve by multiplying both sides by t, doing the same thing to both sides. And so that gives us a distance is equal to the average speed times the time, which is 650 times 4, which is 4 times 600 plus 50. And if we distribute those, we get 2,400 plus 200 equals 2,600. So we're left with 2,600 miles, which means in this entire journey, the total is 2,600 plus 50, or 2,650 miles. And so the question then becomes, what is the average speed? Aha. Well, if we use our formula for the average speed that we just learned, the average speed is the initial speed plus the final speed over 2. Well, let's try to apply it in this case. And if we were to say that the initial speed was 5 miles per hour and the final speed was 650 miles per hour, and we take those two, that gives us 655 over 2, which works out to be 327.5 miles per hour. Well, let's perform a check and see how that works out. We'll do our check, and our check then is our distance equals the average speed times the time. So 327.5 times 16. Now we know that the distance is 2,650 miles. We know that for sure. Well, we could do our little trick, 327.5 times the quantity 10 plus 6. And as we distribute, we'll notice that this 10 times 327.5 is 3,275, which is greater than this number up here, telling us something is really, really, really wrong about this. This can't be a correct way to do it. You may also remember in the previous example, when we used the other formula for this, we got a speed of about 165 miles per hour, the average speed, in our average speed number 1, using that equation. So something is wrong here, and it comes down to when we can and cannot use average speed number 2. The acceleration must be constant. Now, if we consider what happened here, we have Matt starting out. We assume they're stationary. Well, they're stationary. Their speed is 0. And then they speed up and get to some speed. And then they travel maybe at that speed for most of the time. And then they slow down. And then they remain stationary for a while. And then they get on the plane and they accelerate. And then they travel at a constant speed. Then they slow down, acceleration at the end there. So in some instances, in this case, the acceleration is 0, like if they're traveling at constant speed. And then there's times where we have positive acceleration where it's speeding up, and then we have negative acceleration where it's slowing down and so forth. What we can see for sure is that in this case, the acceleration is not constant, therefore we cannot use that formula. So the observation we would make is we can put numbers into this formula. but it won't give a reasonable answer unless the acceleration is constant. And that was our starting point. So we can get an answer that will give us average speeds, but it will not necessarily give us an answer that is correct or true. And that, my friends, is average speed number 2.